Before we discuss Newton's 3 laws of motion, we need to properly define and understand what we mean when we say things like displacement, velocity, and acceleration. Things that all of you have heard of, and everyone has some type of misconception. And I don't care if this is your first time ever heard of these topics, or if you're a physicist like me who's been doing this your entire life, you will have some misconceptions, and we always need to study these things. So, distance. We can talk about the total ground cover. So the example here would be if you, say, climbed a ladder. You went 5 meters forward and 10 meters up. So the distance is that distance, how far you've traveled. But when we talk about displacement, we need to talk about a vector quantity. So as a brief reminder, our unit for distance will be a meter. We measure distances, displacements in meters. And our displacement is this full-fledged vector. If you want to draw it on this picture, it's this guy. There's our displacement vector. All right? So, what do I mean by a vector? I'm talking about something that has a length. In this case, I could say that when I started the base to the top of the ladder, I traveled 11.18 meters. So that's the length of my vector. And it has a direction associated with it. I wouldn't just go to the right and up. I went both. So this idea of a vector has this notion of length and direction. And that's going to be very important to us. If you're wondering why this matters, I hope the next example when talking about velocity, the speed vector, is going to matter. So speed. Easy one. Everyone knows this. It's just how fast you're moving. Unit-wise, it is a meter per second. And if I was to describe the velocity, well, that's the speed and the ever so important direction of your motion. Imagine you want to cross the street. And any car going this direction, you don't care about. They could be going 10 miles per hour. They could be going 60 miles per hour. You just don't worry about them because their velocity, their direction, isn't towards you. Now, when you're trying to cross the street and there is a car going 10 miles per hour towards you or 60 miles per hour towards you, you suddenly care a lot about the vector, the directional part. All right? So, our speed only describes how fast you're moving, 20 miles per hour. The velocity describes not only the speed you're going at, but the direction. Are you going eastwardly? Are you going southwardly? And we care about the vector. Lastly, we have our acceleration, which is defined as just a change in the velocity. Crucial point here, that velocity refers to the speed or direction. So unit-wise, it is a meter per second squared. Another way to say it is a meter per second is another way to describe that. So going back to my tennis ball example, let's pull me up here. On my tennis ball, I'll throw it up, and it will accelerate at 9.8 meters per second squared. So I give the ball a toss. I toss it up. As it goes, it's slowing down, reaches its peak height. The speed is now 0 meters per second. The ball is moving, stops. It's moving, it stops, and now it starts to fall down again. The acceleration during this whole motion is downwards. The ball slowing down, stops moving, starts falling now, going faster and faster, accelerating more and more that direction. The rate of this acceleration on Earth will be what we label as a lowercase g, and it'll be 9.8 meters per second squared. When you roll out of bed and you don't quite catch your footing, you feel that sudden rush as you're plummeting towards the ground. That's g, little g, that 9.8. That's the acceleration you're feeling. So some examples that involve accelerations, they're easy ones, like speeding up if you hit a gas pedal, or slowing down, you hit the brakes. You speed up, you feel yourself lurch into your seat, or you slam your brakes and your seatbelt catches you as you keep trying to go forward, right? Those are examples of accelerations. What about turning, right? Keep your speed constant, but turn the wheel. All of those of you who have ever had siblings in a car ride, or maybe you're riding with your bae and you want them to slide closer to you, you take a sharp turn. You don't change your speed, you just turn rapidly. And you will feel the person or yourself sliding into the door, or sliding into other people, right? So there is this change in velocity. Your vector can change. While your speed remains constant, you can be moving at constant speed, but because you are turning, you are changing the direction of that ever so important vector. If that vector changes, if your velocity vector changes, there is a acceleration. So for the rest of this, when I refer to acceleration in the equations that we're going to show later, we're going to use a lowercase a for acceleration. G is a special case. G is a special case here on the surface of Earth. So with that, let's start moving into Newton's laws. Newton's first law is also known as the law of inertia. This came from Galileo's notions of objects moving at the same rate. Now this is worth me reading out very carefully. Objects at rest stay at rest. Objects in motion stay in motion unless acted on by external forces. As long as there are no external forces, you will move at a constant rate. In this example here, we'll have a vehicle moving with a constant velocity. And at that constant velocity, you could have, say, like your coffee cup, and it's going to be level. It doesn't matter if you are stationary, you're stopped at a red light, or if you're coasting at, say, 100 miles per hour. The speed doesn't matter. The liquid will be level, and you will not have any accelerations. You're going to be moving at this constant rate. If we eliminate all the friction, such as the friction on the tires, then that car will keep moving at 100 miles per hour. As long as as long as there's no forces, it's going to be a constant velocity. Hearing me say these words and remembering them, which I encourage you to do, these laws are important, doesn't really help us comprehend these physical laws. So let me switch over to this video here, where I have Rex sitting on a trampoline. And what's going to happen in this video is that a 30 kilogram ball, basically a gigantic bowling ball, has been thrown a couple stories off of a building here, and it's going to hit the trampoline. The bowling ball is going to have a high velocity, so it's going to move rapidly through the trampoline. Rex is at rest and wants to stay at rest. So there's Rex. The bowling ball has hit the trampoline. Like I said, first law, Rex is at rest and wants to stay at rest. Gravity's now acting on Rex. Gravity is trying to accelerate the T-Rex, and you can see it falling a little bit, but it's not nearly as rapidly as how quickly the bowling ball moved through. Objects at rest stay at rest unless acted on by external forces. That bowling ball is an object in motion, and it's going to stay in motion until an external force, the trampoline, brings it to a stop. One more demonstration of the first law. I got to put myself on the line now. So let's pull me up. So what I have here is a lead brick. Now I can convince you how dense and heavy this thing is. Let's pick it up. Lead is a very dense, heavy material. I'll say it's very massive. Now, the inertia refers to how much is needed to get an object moving. Imagine trying to get a little sports car going rapidly versus a truck How fast does it take a big, massive truck to get to 60 miles per hour? It takes a lot more force. So the mass of an object is related to how hard it is to get it moving. So I've got my lead brick, and I'm going to take a nice little hammer here. And let's put my hand on the line. So I've got my hand placed underneath the lead brick, and gonna give it a little whack. Okay, let's go more. Still going. Nothing. All right. Now let's actually do this. Let's go for some real whams. Really whacking this thing as hard as I can. Just nothing. I don't feel a thing outside of the weight of the brick crushing my hand. But as I try and hit it, nothing. All right. What's happening? What's going on? The lead brick has a lot of inertia, and it takes a lot of force. I need to push very hard, very rapidly in order to get the brick to move. So when I hit it with the hammer, it's just not enough force. The force of my hammer swinging just dings the lead brick. It's not enough force for the brick to translate to my hand and crush my palm. So there's the first law in action, everyone. Coming into Newton's second law, we say that a force causes a change in the motion. Equation-wise, we'd say a external force is equal to the product of an object's mass times its acceleration. Another way to phrase this, the force goes as the inertia and the acceleration. So a force, what are these? Well, they're pushes and pulls, right? How hard am I tugging on you? How hard are you pushing on me? The unit of a force will be a Newton, and this will be a building block that will come up later. We'll need Newtons when we start talking about energy later in this course. And in essence, if there is an acceleration, if an object is speeding up or slowing down, there is some force providing that acceleration. And the coffee cup example again, when you have an acceleration that's causing your speed to increase, the coffee will slosh back. And as you slow down, you apply your brakes. There's your external force. Your brakes cause you to slow down. The coffee cup, the liquid, wants to keep moving forward, so it sloshes forward. So these are very linear examples of accelerating, speeding up, or accelerating to slow down. What about a ball rotating on extreme? Is there a force? Is that accelerating? So let's bring me back again. All right, here's my ball on a string. Is there a force on this object? Yes, there's a force. The force is the tension in the string. Something is trying to stop the ball from going away. So as long as there is a force in this string, the ball will go in circles. So there's a force here. If there's a force, by the second law, there has to be an acceleration. F equals ma. So an object, while turning, right, exactly, you're going forward, and it turns, there is an acceleration. Rotating objects have a force. In my ball on a string, it's the string that provides the force. Now imagine sun, planet. There's a gravitational force keeping the planets bounded to the sun. We can rephrase the second law. Instead of saying F equals ma, instead we could say A equals the F divided by m. The acceleration is the force divided by the mass of an object. Recall that mass is a measure of inertia, how much you resist a change in motion. So if we keep the force constant and we change the mass for a given force, as the mass increases, the acceleration decreases. Greater the mass, the lower the acceleration. Or another way to say that, it takes greater forces to get greater accelerations. The larger the force, the larger the acceleration. To help us visualize the second law, let's go to my favorite hitboxes. Right? So, I've got two boxes here. As far as you can tell, they look the same. They're the same dimensions, same type of box. And I'll tell you that they weigh different amounts. They have different masses. So, I'm going to do an experiment. I'm going to hit them with the same force and see what their accelerations are. Right? So let's hit box 1. All right. Now for box 2. Same forces. Which box is the lighter one? Which one has the lower mass? Well, clearly this one. I hit both of them with the same force, or roughly the same force, and yet this one had a much greater acceleration. Well, from that second law, as the mass decreases, the acceleration is going to go up. We'll do this again, just to convince you. All right. Box 1. Box 2, the same force. Clearly, this box is a more massive box. There is more mass in here. Its acceleration is going to be smaller for the same amount of force. Newton's third and final law of motion is the law of equal and opposite forces. For every force, there is always going to be an equal and opposite one. In the picture here, we have the woman pulling on the rope. So as she pulls on the rope, she's creating tension. And she's feeling a force generated by the heavy object pulling it back, pulling against. Other examples of this, when you go swimming, right, what happens? You are pushing on the water. You push the water when you swim through. Correspondingly, the water pushes you forward. So that's the third law in action. Some misconceptions about this. Motion can't be real. There's always these opposite forces canceling each other out. But what you need to be clear is, although there are equal and opposite forces, they act on different things. Go back to the swimming example. You do your breaststroke. You bring your arm into the water and you apply a force. You push on the water. All right? The third law says the force of the water on you is equal to how much you push on it. But the accelerations can be very different. You go forward. You have an acceleration forward. But the pool itself, imagine how massive an entire pool of water is. The pool is significantly more massive than you. So yes, you apply a force. You push some water, and the corresponding water pushes you forward. Continuing with this type of logic. Without friction and the third law, you could never walk. Here's the setup. You'll have the force of your shoe on the ground and the force of your ground on the shoe, the ground on you. When you step, you take a step, you're applying a force. You are trying to push the ground that way. Now, Earth is orders of magnitude heavier than you. So Earth barely moves, barely accelerates. Think back to the boxes. It's much more massive. But you correspondingly feel a force from the ground on your shoe. And so you get to move forward. It's because of friction and the third law that you can even walk. A thought experiment to apply Newton's third law. Let's say I or some evil scientists have trapped you on a frictionless material. So there is no friction between your shoes and this disc of material. There's no way for you to walk off. There's nothing for you to push off of because we are canceling the third law with this frictionless substance. So how do you escape from this predicament? How do you get out of this trap of this fancy ice rink? All right. Well, even though you can't walk, you still could throw something. How does a rocket propel itself? Think about that. What does a rocket do? Well, you put some material. For boosters that go into space, you use a liquid substance. I'm just going to use air pressure. All right? There's a bunch of pressure in here, and it's going to, when I release, start to escape, fly off. So, third law happens. Little gas are trying to escape out by pressure pushing them out. They'll correspondingly push the balloon off the screen. So, when you throw something, you are accelerating that material. It correspondingly pushes on you. So, by the third law, if you were stuck on this ice rink, take off a shoe. Throw your boot. The boot will have a high acceleration relative to you because it's way less massive, but because the boot will apply a force on you from the third law, you will slide in the opposite direction that you threw your boot, and you will slide off safely to the edge of this frictionless material. Summarizing all of this, Newton's laws. There is the law of inertia, that objects resist changes in their motion. The second law is always just referred to as this F equals ma. The force is dependent on the mass and acceleration. And the third, every force has an equal and opposite pair. Now, one thing we'll show in later sections is that Newton's laws are able to predict all of Kepler's laws. Kepler's are just a subset of Newton's predicting capabilities. Finally, summarizing everything in this section, retrograde motion, the motion of the planets, it can be explained by removing the geocentric model, putting the sun. You shift to a heliocentric model, a sun-centered solar system, and you can easily explain retrograde motion due to the planets and Earth orbiting the same object. Copernicus was one of the biggest supporters of this, and that led through a string of different people throughout the ages. Copernicus, Tycho Brahe, Johannes Kepler, Galileo, Newton, all of them making incremental steps, incremental improvements in our understanding and knowledge. So, with that, this will be the end of section 3. I'll have a good time.